Welcome to this session. This session is the second installment in working thermodynamics free response problems in which you do not have a calculator in your hand. So look, Ma, no calculator. Now, doesn't mean you're not going to do math, and this is a perfect example. So as I've said before, if you listen to the first recording, this is where you should be starting. Listening to the essay portions of each unit is where you should start, because that's where the conceptual learning occurs, and that's going to translate into a lot of multiple choice points for you. There are certain ways we test in the free response that are designed solely for the free response because it's the only time you have a calculator in your hand. These sorts of concepts, like I say, I can take any one of these essays and write about 8 or 9 multiple choice questions from it, so it's a good thing that you're here. Now, having said that, I also want to encourage you to not listen to every morsel of this, because some of this is bound to be sinking in sooner or later. We're all capable of learning, just comes down to how many repetitions we need. So you never hurt my feelings, because I'll never be the wiser if you fast forward through things that you already know, if you back up and rewind and listen again to try to understand what the heck I'm saying as well. And then, as always, I encourage you to ask questions of your teacher. That's why you have a teacher. I never, ever, ever want to replace your teacher with these recordings. So let's get at it. We are moving into the 2000s, and so this particular essay was from the year 2000, Y2K, much hysteria. Everyone thought everyone's computer was going to come crashing down on New Year's Eve. But as it turned out, it didn't happen. So when we look at this was a 10-point question. We have everything in terms of gases. So I see this delta H right here right away and know I'm in the land of thermo. So I want to look back up here and go, let's think about these states on these critters that are reactants and these critters that are products, and say, all right, we have 2 moles of gas going to 2 moles of gas. What that means is that delta S, the change in delta S, is approximately 0. It won't be exactly 0, but it's dang close to 0. So if you're asked, just say it's approximately 0. That may factor in, because that means that in the granddaddy equation, delta G equals delta H minus T delta S, formerly known as the Gibbs free energy equation. I just think granddaddy's way more fun. The T delta S term is going to go to 0 once you multiply a near 0 value for delta S times T. You'll be subtracting essentially nothing. So the delta H, the enthalpy of this reaction, is definitely a driving force if I'm asked. I haven't even read a question yet, and I've already got several points on the board. So let's go ahead and read the question. Referring to the data in the table below, calculate, even though you don't have a calculator, the standard enthalpy change for the reaction at 25 degrees Celsius. Be sure to show your work, because that's where the points are going to be added. So delta H naught is equal to, now we do Big Mama equation, Hess's law formally, the delta H naught, I hate it when my pen does that, delta H naught of the products minus the delta H naught of the reactants. So looking at this, I need to realize, first of all, there's a celebration moment in the fact that that delta H is 0, because that's an element at standard state. Ozone, however, is not. So the only product that I have is the value for NO2, which is 33. So 33, and I'm not going to do units now. I know that all of the units come out kilojoules per mole when I'm finished adding and subtracting and multiplying. Minus the sum of the other 2 reactants, which is ozone, which is 143, and NO, which is 90. And even without a calculator, I can say that's 33 minus 233. And so that's going to equal minus 200, just grab the units, don't get creative, kilojoules, mole to the minus 1, you can write it kilojoules per mole, doesn't really matter. What matters is, A, you got 200, and B, you got minus 200, because this is an exothermic process. And so indeed, this was a 2-pointer. Oh, I take that back, it was a 1-pointer. They just gave 1 point for that. So that minus sign became even more important, because you either got it or you didn't. Then they want us to make a qualitative prediction about the magnitude of the standard entropy change. See? Knew it was coming. Delta S naught for the reaction at 25 degrees Celsius, and justify your answer. So this really should read B, part B, and it's 2 points. And we already did this, but I'll put it down in formal language. Delta S naught will be near zero, since the number of moles of gas on each side of the equation are the same. Therefore, the amount of disorder did not appreciably change. All right, big people word appreciably didn't change a bunch is what it translates into. And you probably could get away without even having the stuff after the therefore, but you know, I'm supposed to be modeling the best behaviors here, so I'm going to try to get you to give the most complete answers. Did that with my own students, and that's what makes the difference between teaching to a 3 and teaching to a 5. And so I want you to get the 5. I want you to have a good shot at getting a 5, because universities are getting pickier and pickier about what they take. So having said that, by the way, if you haven't done that, you should go out and look at your favorite universities, the places where you think you want to attend, and go to the AP Scores section of their website and see what you need on this exam to get credit for the universities that you wish to attend. 3 may not cut it. You may need 4s and 5s. All right, moving on. Oh, that was 2 points. Let me do the breakdown on the 2 points. 1 point for saying it was near zero. And if you said 0, that's okay. And then a second point for why. So for the explanation, the number of moles of gas on each side are the same. Got you the other point. And as always, you know now to pause these. You shouldn't just be watching me work these. That doesn't do you any good, because I kind of know how. So I want you to kind of know how. So you should work these prior to listening to me work through them. Lots of stops and starts, but it's good for you. All right, on the basis of your answers to part A and B, predict the sign of the standard free energy change, delta G naught, for the reaction at 25 degrees Celsius, which they're just telling you it's standard, and explain your reasoning. All right, easy enough. Granddaddy moment. Delta G naught equals delta H naught minus T delta S naught, which we just said was 0. So that's going to be a negative value for the delta H. How do I know? Because I calculated a negative value up at part A, which brings up the question for you that, well, what if I didn't put that negative sign on? Well, if you come down here and put a positive sign on and answer this question in that context correctly, you can still recover all the points on this part C. Minus T, which is a positive value, delta S, which is a 0. So this entire term goes to 0. So we're subtracting 0. Therefore, delta G naught will equal a negative value. All right, so that's all they really wanted. So they want the calculate 1 point for saying it was negative and 1 point for the calculation. So this was a 2-pointer. So 1 point for saying negative and 1 point for showing how. All right, so you could also have done it in words. I could have, like you heard me verbalize what I was doing, I could have just written sentences to basically explain that you would be subtracting 0 from the negative T delta S term. We calculated a negative delta H on part A. Therefore, since delta G now is equal to delta H, then that means that, essentially equal to delta H, I should say, that means that both values must be negative. That should be D. Use the information in the table below to write the rate law expression for the reaction and explain how you obtained your answer. Okay, this is typical of a more modern problem now that we've entered the 2000s. They're going to wrap a piece of electrochem, a piece of kinetics, or something else into this situation. You may not have studied kinetics yet. That's okay. You can stop right here and say, you know what, I'm going to come back to this piece of this problem after I learn how to do this. I'm going to go ahead and work it, just in case your teacher was not following the NIMSY pacing guide that we suggest and has done kinetics prior to thermo, because if you march down the table of contents of a general chemistry textbook in college, that's how it is. But we know in a student's brain it's better to put the enthalpy with the entropy and the free energy instead of waiting about 8 chapters in between the two concepts. So we've rearranged the sequence of events a little bit. So If that's the case, you haven't done kinetics yet. But if your teacher's not following the pacing guide that we put out, then you may have. So either way, either make a decision to skip through this piece or listen and learn. I'm looking for an experiment, since I have 4 to choose from. I want a pair where something was held constant, anything. And so I could have either used the top 2 lines or the bottom 2 lines. It doesn't matter. I get the same concept going on the other side with NO anyhow. So in experiments 1 and 2, concentration of ozone is held constant, while the initial concentration of NO is being doubled. And I ask myself, what happened to the rate as a result of that? Well, the rate wasn't given to me in numbers, it was given to me in variables, but they called experiment 1's rate x, they called experiment 2 rates 2x, so what that means is there's a direct relationship here. So if I double the concentration of NO, the rate doubles. Well, that's what we call first order, and so that means that I have a exponent of 1 on the concentration of NO in the rate law. So same song, second verse. Now what I want is to find a place where this concentration was held constant. So I'm going to focus on experiments 1 and 3 in purple here. And I ask myself, what happened to the concentration of ozone from experiment 1 to experiment 3? Well, it doubled. So that doubled. And then I ask myself, 1 to 3, what happened to the rate? It also doubled. So that means this is also first order. So now I can write the rate law that they want me to do, rate law expression. Rate equals K. You always start that way. Concentration of O3, and we know that's a 1. Concentration of NO, and we figured out that was a 1. No, you don't have to write the ones. The ones are understood. I put them there for emphasis. And then they want me to explain how I obtained my answer. So I'm going to now put into sentences what I just did. Experiments 1 and 2 held concentration of ozone constant while doubling concentration of NO. The rate doubled. Therefore, first order in NO. All right, I really wish I had done that in blue so it matched what I did above, so forgive me for a moment while I correct that. Love this machine. All right, I'm going to continue with purple now. Okay, so everything I did up on that table in blue, now this sentence matches. And so experiments, what did I use? 1 and 3? 1 and 3 held concentration of NO constant while doubling concentration of O3, the rate doubled. Therefore, also first order in ozone. That looks like C or something. Okay, so that's where I got those exponents. That is a classic. That is a classic, and that classic was worth 3 points. So that's easy greasy kinetics. It doesn't feel so yet. That's because you haven't studied it yet, but it will feel that way soon. So this was worth a point. There are recordings on those already done as I speak to you today. 1 point for the explanation of how we got the exponent on the NO, 1 point for the explanation of how we got the exponent on the ozone. Part of that chapter is also about mechanisms. So now that we have just come up with an experimentally determined rate law, that's what that thing in that red box is. It's an experimentally determined rate law. We need to have a mechanism that supports it, matches it, etc. Again, that's another whole lesson, another whole chapter. The following 3-step mechanisms proposed for the reaction identify the step that must be the slowest in order for this mechanism to be consistent with the rate law expression derived in Part D and explain. There's a whole video on just mechanisms. So if you know how to do it, this one was pretty straightforward. If you don't, then listen and learn. One of the first things you want to do is make sure that you regenerate the stoichiometry of the equation given at the top of the page. So I'm looking for ozone plus NO yields O2 plus NO2. Otherwise, I can void this mechanism right off. So that is an intermediate because it's formed and destroyed in a subsequent step. That drops out of my equation. NO3 is an intermediate, also formed and drops out in a subsequent step. So I get 2 O3s plus 2 NOs yields 2 O2s and 2 NO2s, which simplifies to my original equation. So the stoichiometry is indeed respected, and that means that it's worth analyzing further. So then I look at step 1, and now that I've gotten the intermediates and stuff out of the way, I look at what is reacting in step 1, and I write a molecularity-based rate law expression for this. So rate equals K. Don't try to make this hard. Just pick those babies up. There's only one of each of them, so they are first order in this. I'm going to put a 1 on that because it's not the real K. And NO. Or I don't know if it's the real K or not yet. I haven't determined that. Well, at this point, I've actually regenerated, just with step 1, my experimentally determined rate law. So that is the slowest step, the rate determining step. So this is my slow step. And they want me to explain. So my explanation hinders on the fact that step 1 is the rate determining step, since its rate law agrees with the experimentally determined rate law. And I've shown my work to support that, or else I would write what it is right there in that spot. And then I think it's just good form to kill off why the other two cannot be correct. Because if the slow step, so synonym, slow step, rate determining. Big people words, rate determining. Common sense, slow. If the slow step were step 2, then the mechanism, I still want to put the two words together, stop at the mechanism would yield a rate law of rate equals K, concentration. Now look at this one. This one would say rate equals K2 of O3, and I want you to picture my first 2 fingers on each one of my hands making quotes in the air, which I call air quotes, making little air quotes to say we're going to add these together. If we did that, then ozone is bimolecular and would have an exponent of 2, and NO is, there's still just one of those, so it has an exponent of 1. If the slow step were step 3, then the mechanism would yield a rate law of rate equals K. They all start that way. Now look, that was left standing, so that's why we put that one over here. Now what is this one going to be? Rate equals K, concentration of NO, period. So now if I add all 3 of these together, again, air quotes, we're not really adding them. Okay, we're just compressing them, collecting them, just taking into account all the collisions that would happen in this mechanism. Then we come out with rate equals K, and it would be O3 squared and NO squared, which begs the discussion that if you goofed up back up here in blue and you didn't get rate equals O3 times NO both to the first order, and you had one of them as a second order, and you come down here and you choose the mechanism that agrees with that, you still get all these points. There's no double jeopardy on this exam. Okay, so I need to point out why It's one thing to tell you what, and it's another thing to tell you why. So I can tell you what it would yield, but I need to tell you why that's not right. And the reason it's not right is it does not agree. Neither agrees with the experimentally determined rate law that I got. All right, so that was worth 2 points. 1 for getting step 1 and 1 point for the argument. And again, if you want the 5, you need to be very complete in those arguments. And do agree with yourself. Don't contradict yourself. Actually read what you've written. I realize it costs you about 15 more seconds, but read what you've written. I can't tell you how many kids say, oh, this is going to increase, and then give me a beautiful argument for why it would decrease. So you don't get points for that. All right, so that was 2000. So let's venture into 2003. I'm going to make another copy. I've learned to do that so that I can just go back and delete the messy one instead of spend a lot of time trying to erase everything I've written all over it. All right, so this particular question is an 8-pointer, which is typical when you don't have a calculator in your hand. Sometimes they're 9 or 10, but more often they are 8. All right, so this one is kind of nice because, again, we have a table of information and we have a very simple equation. 2 nitrogen atoms, therefore they're not bound, okay? 2 nitrogen atoms combine to form a nitrogen molecule, which does have a bond, as represented by the following equation. Matter of fact, it has a fabulous triple bond. Using the table of average bond energies below, determine the enthalpy change, delta H, for the reaction. You should know that among all those diatomics, everybody is singly bound except this guy and this guy. This guy looks like this with its Lewis structure, and this guy looks like this with its Lewis structure. You just need to know that. There's some stuff you just need to know. And so when they have this right here, my brain is thinking triple bond and no bonds. All right, so using the table of average bond energies to determine the enthalpy change for the reaction. Well, delta H equals the energy of the bonds broken minus the energy of the bonds formed. Well, you didn't break any bonds, so that's 0 because those were atoms. So this is a pretty easy question. I know it's triply bound. I put a minus sign on the 950. I grab the units and don't get creative. And I'm done. There's my answer. All right, how much did I get for that? I got 2 points for that. I got 2 points for knowing it was a... Oh, I didn't write it down right, though. Very helpful to add that 0 on there. Got ahead of myself. Got so excited about how easy it was. Okay, so I've got a point for getting the 950 for the magnitude. In other words, knowing it was a triple bond, not a single, not a double. And a point for the sign, because energy is released when bonds are formed. It costs you energy to break bonds. And you didn't have any cost. All you had here was payoff. So that 950 kilojoules per mole left the system, hence the negative sign. Then they go on to give me a value for the delta H. So my delta H bears a negative sign. So this is exothermic. So I can also be thinking about this as the fact that I would add onto this reactant, or product side rather, that many kilojoules of heat. So predict the sign of the standard entropy change for the reaction and justify your answer. All right, well, there's 2 ways you can do this. The first way is the whole mole of gas way, which is the really easy way, but you could have also done this through the math. I'm going to go with the easy route because that's what I want you to always do. I'm looking at this equation and I'm seeing, hey, you're asking me about disorder, so it's all about the moles of gas, solid or liquid on either side. If they're kind of the same, then we don't get much hint. You know, it's pretty much a wash, and we say that delta S is essentially 0, but that's not the case here. I have 4 moles of gas going to 2 moles of gas. That's a big drop in disorder. So negative delta S naught, get your prediction right up there at the beginning. That's a drop. My key says positive delta S, which is freaking me out a little bit. Let's It's a drop-in disorder, though, so it's negative. Since the products are more ordered than the reactants, as evidenced by 4 moles of gas, 4 moles of gas reactants producing or forming, you can pick your verb, 2 moles of gas products. Definitely a decline in disorder. It's getting a little crowded, so let me just widen that out just a little bit for you. Okay, now what? Now we want to say, what is the value of delta G for the reaction represented in part B? It is negative. The value is negative, so they're telling me negative delta G at low temperatures but positive at high temperatures, and explain. Well, delta G naught equals delta H minus T delta S. What did we just figure out? We just figured out that delta H is negative because they told us that way back up here, right there, minus T, which is always a positive value, so I'm going to put a positive there, times, what did we just say? We said this is negative. So I have a negative term minus another negative term. So what's going to happen? As temperature increases, that T delta S term, which is negative but subtracted, so it's going to be a positive overall entity. That's going to actually switch my negative delta G over to a positive once the temperature increases. So as temperature increases, and you can write it that way, the T delta S term also increases. I should say the negative T delta S term also increases, but is subtracted. So once its value exceeds negative 92.2 kilojoules, the value of delta G becomes positive. Notice I said exceeds, because if I said it was equal to that, then delta G would be a flat-out 0 and would be at equilibrium. So choose your words carefully. You've got to go past that point of no return for delta G to become positive. Okay, I'm not always good in my scribble about putting all of that stuff in there, so forgive me for that. You should do what I say, not what I do. Isn't that how that works? And your mom ever said that to you? I don't know what's up with my software making everything an A, but it's been doing that lately. All right, so finally, when N2 and H2 are placed in a sealed container at low temperature, no measurable amount of NH3 is produced, and explain. So at low temperatures, what's going on? At low temperatures, no NH3 is produced. All right, so we're back to activation energy. We're back to this concept that we've encountered in the first video on this, that this is the domain of thermo. We know we have an exothermic reaction here. So we know we started off with our products at a higher energy than our reactants, and that energy left the system. How much energy? The difference between here and here is equal to our delta H, and we put the negative sign on it because energy left. The reason this doesn't happen immediately when you put these things into a container is that there's an energy barrier that has to be overcome called the energy of activation. That's what we're going to study in kinetics. And in biology, we're introduced to this concept, and maybe other science courses as well, and we can put a catalyst in and we can lower the activation energy. But the activation energy, uncatalyzed, is from there to there. Catalyzed gets lowered from there to there. All right, so any way we look at it, we need to explain it, the whole point of this question is, do you understand that you got to overcome activation energy before you get anywhere? So at low temperatures, And temperature is defined as the average kinetic energy of the molecules. So the kinetic energy average of the molecules is low. Thus, a smaller fraction. Because you know what average means, right? Some things are above the average, some things are below the average, but it all averages out to the average. So a smaller fraction of the reactant molecules are of the average above, the kinetic energy above the activation energy. Smaller fraction of reactant molecules have sufficient, another big people word, sufficient energy to overcome the activation energy. Therefore, few reactant particles collide with enough energy to form products. So we're in the land of heat 'em up, speed 'em up. If you heat them up, then they're going to collide with more energy, and there's going to be more molecules with sufficient activation energy to get over, and you'll see this reaction go faster. So low temperature, sluggish molecules, no measurable amount of product is produced because you don't have very many that you could see actually create the new product. And in this case, I don't think you'd see it as much as you'd smell it, because you're going to make ammonia gas. Stinky stuff. All right, so these last two parts were also worth 2 points each. This is a typical, I don't have a calculator in my hand, there's 4 parts to the question, a what and a why. So just to make sure you understood the scoring, that was worth a point. The explanation was worth a point. That's the what and the why. For this one, you got 1 point for using this relationship. So use the granddaddy equation somehow, and 1 point if you actually made sense of the math and wrote a sentence that explained it. And down here you get 1 point for talking about at low temperatures there's a small fraction of reactant molecules with sufficient energy. So this piece was important, and this piece was important, connecting it to activation energy, however you worded it. Therefore, there are few particles that collide with enough energy to form products. So this piece got you the other point. Okay, onward. Again, I say, make sure you have worked these before you just sit and watch me work them, because I know how. The point of these is for you to know how. Well, that's all crowded up there, but what have they given us? They have given us, why don't I have an answer key to this one? Hang on a second. Did I get them out of order? Because I want to give you the point values here. Ah, there we go. I'm organized again. All right, so here we have definitely thermo moment, delta H, delta S. The only thing missing from this party is delta G. So it's worth, before you even start reading, thinking about what's going on with the entropy. And we know it's negative, but we may be asked to explain why. So this is 3 moles of gas, and this is 1 mole of gas. That would be why. And then it's endo, but yet it has the proper, nature. Well, now it's got a negative delta S as well. So this is going to be interesting. All right, I'll answer the following questions. On the basis of thermodynamic data given above, compare the sum of the bond strengths of the reactants to the sum of the bond strengths of the products. Well, again, enthalpy can be deduced from bond energies. And you know that delta H is equal to the sum of the products minus the sum of the reactants when we're given heats of reactions. But you need to think about the fact that when you talk about bond energies, it's cost versus payoff. It costs you energy to break bonds, and you get energy back when your product molecules form. So the fact that this is an energy hog and it's an endothermic reaction means that energy was taken into the system to break the bonds, but the ones that were formed weren't as strong, thus they didn't release as much energy. All right, so we got to just put that into words. So delta H is positive. We know that. You're not going to get a point for that because they showed you that right up there. So delta H is positive. Therefore, energy, that's what you got to talk about, energy was taken into the system to break bonds. Energy is released when bonds form. So I'm going to put a period there and start a new sentence. So the sum of the bond energies of the reactants are greater than the sum of the bond energies of the products. All right, because that's what they asked me to speak of, the sum of the bond strengths. I used energies, but same thing. All right, then let's see about the next piece. Does the entropy change of the reaction favor the reactants or the products and justify your answer? Well, the entropy change favors the reactants because you got more chaos, more disorder on the left than you do on the right of that equilibrium sign. So the entropy change favors the reactants. Think favors the side with the most chaos, since they are in a less condensed state, which means they're more disordered. And then you need to really talk about the moles of gas on each side. So that's the favored state. So you can do it with some diagrams and things to kind of help explain, but the big idea, again, is that 3 moles of gas, more disorder than 1 mole of gas. So this is that equilibrium is going to shift to favor that 3 moles of gas when it has an opportunity to do so. This is part C, and this is part D. All right, for the reaction under the conditions specified, which is favored, the reactants or the products? That's what I just explained. Knew that was coming. Justify the answer. Okay, reactants are favored. Since delta G is positive. Or non-spontaneous. How do I know that? Back up to the top. I don't know that. I have to figure that out. Delta G equals a positive delta H, that I do know, minus T, which I know is positive, and a negative delta S, because they gave us that too. All right, so what does that mean? That means I have a positive delta H term plus a positive T delta S term when the minus part is taken care of. So positive delta H plus T delta S algebraically, right? And that means delta G is always positive. Therefore, the reaction is not spontaneous. In the forward direction. Okay, so this is one of those cases where you may have written the first part last after you thought through the math part of it. So you really have to embrace the granddaddy equation. You really have to be ready at any time you have been given delta H and delta S, or any two of the three players in granddaddy. You really have to be ready to deal with that through the Gibbs free energy equation, which again, I lovingly call granddaddy, but please don't call it that on the AP exam. It's very embarrassing. That's our secret. We just do that, you and me. All right, so now explain how to determine the value of the equilibrium constant for the reaction, but do not do any calculations. This is awkward. This is very awkward. It's hard, I know, for most of you because you're pretty mathematical or you wouldn't have signed up for this course to begin with, even if you don't want to admit it. But when they say explain how, that means we need sentences. That doesn't mean just sit here and do the math for me. We want to make sure you've internalized how. So we know what to do, right? We were given delta H, we've been given delta S. We would have to actually solve for delta G, because what you know that relates K to any of this thermo stuff is minus Ratlink. So you're going to have to use minus Ratlink, but you can't use minus Ratlink until you know what delta G is. So step 1, solve for delta G. Solve for delta G using delta G naught equals delta H naught. I probably should put a naught on here too, shouldn't I? Minus T delta S naught. Using this and values given at the top of the page. Or you could just say given. You don't have to do that at the top of the page part. Delta H naught and delta S naught. You know that T equals 298 Kelvin. All right, so next sentence. Once I get delta G, what the heck do I do with it? Next, solve for, I like to solve for ln of K, but you can go ahead and go straight to K if you wish, using delta G equals minus RT ln KEQ, where R equals 8.31 joules per mole Kelvin, and T equals 298 Kelvin. We already said that once, but doesn't hurt. Therefore, KEQ equals base E, because that's what natural log is. It's not log, it's ln, so it's base E, not base 10, to the minus delta G over RT. So where did I get that? I'm solving for ln KEQ, so wouldn't that be take both sides of the equation, divide it by minus RT, so I get delta G divided by a minus RT. I just put the minus on the outside of the parentheses of that expression, and I'm done. So they want to see if you can actually talk math, not just do math. Now, predict whether the value of KEQ for the reaction is greater than 1, equal to 1, or less than 1, and justify your prediction. Well, if delta G were 0, KEQ is 1, and I do a happy dance because that would be a very easy question. But we just got through saying on an earlier part that delta G is always positive, which it's not equal to 0 in this case. So what does a positive delta G means? A positive delta G means that you ain't going forward very well. So that means you're not making many products. And so when you talk about the fact that KEQ is generally a ratio of products to reactants, then you got a big denominator and a very small numerator, so KEQ would be less than 1. So a positive delta G value indicates that KEQ is less than 1. Then you have several different ways you can justify that. So you can go back to what you just did, that the ln of KEQ, or you can go straight to KEQ if you're good with logarithms. I just find that most students mess that up. You're always going to have a positive delta G over a negative positive R, because R is always positive, 8.31 joules per mole Kelvin. And a positive T, because you know that's always positive. So therefore the negative, you get a negative term for the ln of KEQ. Therefore, for the natural log of KEQ to be a negative number, the KEQ must be less than 1. Now, this connects to the Nernst part of your brain. You've done electrochem, you've done the Nernst equation where we talk about Q and the log of Q. This is the same sort of thing. If you have a negative term for the natural log of KEQ, then that means that your KEQ was a number less than 1. All right, where should we go next? That was 2004. I think I'm going to stop here so that this file stays small enough that I don't have to split it, which makes way more work for me. You never know the difference, but way more work for me. And we will carry on and work the rest of the essay problems, which are, I guess, they're about 3, if you are up for it. And again, I appreciate you. God love you if you stayed to the bitter end, and I hope you have a great rest of your day.